Now, I just want to mention that this process of constructing the sampling distribution of the sample mean to gain more information about the mean of the original distribution, we can do that same thing of constructing sample distributions for the median, the variance, and then sample proportion, any other sample statistic. So the only difference is that in this column here, instead of doing the mean, we would do the median, or do the variance, or do sample proportion for repeated samples. So in each case, we would get a different distribution. It wouldn't be the same distribution, but those would all be sampling distributions. So we're going to concentrate, though, on the mean, though. So what properties do these sampling distributions have? So we've seen some of the properties already. So first of all, I want to define a point estimator. So a point estimate of a population parameter is either a rule or a formula which is going to tell us how to use sample data to compute a single number that estimates a parameter. So we had talked about point estimates. So for example, X bar is a point estimate of the mean, and the sample standard deviation is a point estimate for sigma, the population standard deviation. So these are one number that's estimating the population parameter. That's a point estimate. A point estimator is a rule or a formula that's going to tell us how we can take a sample and compute that single number. Now, a biased estimate is when the mean of the sampling distribution is not equal to the population parameter. So the population mean, for example, if we were doing the sampling distribution for the mean. So in this case, this is when the mean of the X bar distribution is not equal to the mean of the population. That's going to be a biased estimate. And then an unbiased estimate is when your mean of your sampling distribution does equal the population parameter. So the mean of the sampling distribution of X bar, sampling distribution of the sample mean, is equal to the mean of the population. That's unbiased. So we want unbiased estimates. So we want this to be true like it was up above. So just to illustrate this here, if you have an unbiased sample statistic that's trying to estimate your parameter theta, this is your sampling distribution for the sample statistic. Okay, so this is the sampling distribution. And then you can see the mean of the sampling distribution ends up being the population parameter. That's unbiased. However, here's a biased sample statistic. So here's your sampling distribution again, given by the formula f of b. B is your data. The mean of the sampling distribution is in the middle of this symmetric distribution, but over here is your population parameter that it's trying to estimate. So that's going to be a biased estimate when the mean of your distribution is not equal to the parameter. So we talked about means. What about spread? What about the variation in the data? Which type of estimate is going to be better? So, well, let's say we have two sampling distributions here. So this is the sampling distribution for statistic B. And then this one is the sampling distribution for statistic A. And then down here is our parameter value right at the mean of both of those. So we want to know which estimate is going to be a better estimate in terms of spread. Well, it's going to be the narrower sampling distribution, because here the standard deviation or the variation is less. So we'd like to have an unbiased, both of these are unbiased estimates, but we'd also like to have a smaller standard deviation, less variation. Less variation is always better. The measure for variation for a sampling distribution, we call that standard error. it is a standard deviation. So the standard error of the statistic is just the standard deviation, but of the sampling distribution for that statistic. So for example, we'll write things like this: sigma with a subscripted x bar, and that is going to be the standard deviation of the x bar distribution. So it's the standard deviation of a sampling distribution as opposed to sampling standard deviation of the original data. So that's what that symbolism means. Now remember here, for any random variable, that the variance is the sum of the deviations of the data value from the mean squared times the probability of that value. And then the standard deviation, you just take square root of that. So let's say that we're given the following distribution of x values. We've got 0s, 1s, and 2s, all equally likely, so they have probability 1/3. And we want to find first the mean of the original distribution, so that's the expected value of x, which is the sum of x times p of x. So we multiply straight across. 0 times 1/3 is 0. 1 times 1/3 is 1/3. 2 times 1/3 is 2/3. We add those up, we get 3/3, or 1. And so the mean of our distribution is 1. So that's the mean of the x values. Now, if we find means of all samples of size 3 and find their probabilities, we're going to get a sampling distribution for x bar. And that sampling distribution I've actually already found for us here. So here's that, all the samples of size 3, and then we look at the possible means of those samples. The only possible means for samples of size 3 are 0, 1/3, 2/3, 1, 4/3, 5/3, and 2. And then these are the probabilities with which those means occur. So these two columns, that's your sampling distribution. And then if you multiply straight across, you get these products, you sum them all up, and you get 1. So this is the sum of x bar times the probability of x bar, which is the mean of our x bar distribution. Now, if you do medians of samples of size 3, the only values you can get are 0, 1, and 2. And then the probability of those occurring, so if you count up how many samples, there would be 27 samples. How many give you a median of 0 is 7. 13 of those samples give you a median of 1, and 7 give you a median of 2. And then to find the mean of this sampling distribution, that's the sampling distribution for the sample median. You multiply straight across and add them up. And then this is our sum of the median times probability of the median, which is the mean of the sampling distribution for the sample median. So I'll write that as mu sub m. So then if we do an extension table here and find the sum of the x bar values minus the mean of the x bar distribution squared times probability of x bar. So again, this is the standard deviation formula. We'll get sigma x bar is 0.47. So the standard deviation of the x bar distribution is 0.47. If we do the same thing for the sample median, we get the standard deviation for the sampling distribution of the sample median to be 0.72. So the question is, which estimate is better? Well, they both estimate the center properly. They're both unbiased because our original population had a mean of 1. So both of these means equal the mean of the population. But the sampling distribution for the mean has a smaller standard deviation, 0.47. Okay, so x bar is better. And that's because the standard deviation for the x bar distribution is smaller than the standard deviation for the median, for the sampling distribution of the median. So, and we want smaller standard deviation, that's less variation, more accurate estimates. Now, just so you know, I'm not going to have you calculate these standard deviations from the formula, but I will have you forming the sampling distributions. But we've done one example like this all the way through already. The only difference with this one is that you're doing samples of size 3 instead of size 2. So you've got 3 elements for the first number in the sample, 3 choices for the second number, and 3 choices for the third. 3 times 3 times 3, there's 27 possible samples.